Hey there. Forgot to move my head. It's dark over here. I don't think it's going to help. So we are in lesson 10 of unit 2 in algebra. We're connecting equations to graphs. Graphical representation is really important because it can really bring some life to our equations. That's weird. Okay. So let's jump in. Let's investigate what graphs can tell us about the equations and relationships they represent. To warm our minds up, Jada has $20 to spend on games and rides at a carnival. Games cost $1 each and rides are $2 each. So I have games are $1 each and rides are $2 each. Which equation represents the relationship between the, dismiss. The relationship between the number of games, which is X, and the number of rides, which is Y, that Jada could do if she spends all her money. Okay, so this is just number of games and number of rides equals 20. All right, she has $20. This doesn't represent dollars at all. It just represents number of. Okay, if we take the number of games and multiply it by $2, then we know how much money she spent on games. Multiply the number of rides. Oh, no, that is not true. Games are $1 each, so that doesn't work. Rides are $2 each, so that doesn't work. Here we go. Games are $1 each. By the number of games will give me money. And then $2 each for the number of rides, that will give me money. And we know she spent $20. So C is the correct one. Explain what each of the other two equations could mean in this situation. They could mean that you're wrong. Just kidding. Not really. Here, like A, let's say Jada spent $20 and games and rides are $1 each. And then B, Jada spent $20 and games are $2 and rides are $1. Okay, that's what it could represent. It doesn't represent our problem, but it could. And then C is the correct one. Here are the three equations. Each represents the relationship between the number of games X and the number of rides Y. Games is X, rides is Y. And the dollar amount a student is spending on games and rides at a different amusement park. Equation 1, 2, and 3. Your teacher will assign you or ask you to choose 1 to 2 equations. For each assigned or chosen equation, answer the questions. We're going to pick 2. I'm not going to pick equation 1 because it's a bit simplified. I'd like to do something just a little more tricky to push you guys along a little bit. So we're going to look at equation 2 and equation 3. I need to find it in my paper because I'm going to turn the page or move the slide up and I won't be able to see it anymore. 1 second. All right, so we're going to do equation 2 and equation 3. So let's go ahead and you're going to work right along with me. I'm going to write my equation here, which is 2.5x plus y equals 15. Okay, and x equals games. And y equals rides. Let's put it up here. And then when I'm done writing, I'm going to go back and make sure that's correct. Games is X, Y is rides. Cool. Okay, so what's the number of rides the students could get on if they don't play any games? Okay, so if there are no games, that means that this is 0 and y equals 15. So if rides are $1 and they have $15 and they don't play any games, you can ride 15 rides, right? So that's the number of rides the student could get on if they don't play any games. Not $signs, sorry, 15 rides. On the coordinate plane, mark the point that represents this situation and label the point with its coordinates. So the number of rides, 0 games, and 15 rides. And the coordinate would be 0, 15. What's the number of games the student could play if they don't get any rides? So if I have 0 rides, I'm going to take 15 and divide both sides by 2.5. So I'll divide by 2.5 here, divide by 2.5 there, and I get x equals 6. So right there, that would be 6, 0, 6 games, 0 rides. Okay, cool. Okay, what's it going to say to do next? Draw a line to connect the 2 points you've drawn. My line is not going to be very straight because I have this pen and it's hard to draw a straight line. So there is my straight line. Complete the sentences. If the student played no games, they can get on 15 rides. For every additional game that the student plays, X, the possible number of rides, Y, increases or decreases. For every additional game that the student plays, the possible number of rides decreases. Let's see. For every additional game the student plays X, so every increase in X, they get to play, I think, 3 less. 15 divided by 6, 2.5. Yep, I'm sorry. Silly me. 2.5 really isn't a... So for every additional game that the student plays X, the possible number of rides Y decreases by 2.5. It should go right there. What is the slope of your graph? Where does the graph intersect the vertical axis? So the slope, if you remember, that's change in Y, that's what that triangle means, over change in X. So I can take change in Y, so I go from, let's say, if I take these 2 ordered pairs, I'm going to do 15 minus 0, so that's my change in Y, 15 minus 0 over 0 minus 6. And that's going to be a negative 2.5. That's the slope of my graph, and that symbol is M for slope. And then where does the graph intersect the vertical axis? It intersects at 15. So the slope of the graph is right here, and intersect the vertical axis at 15. Okay? Now it says rearrange the equation to solve for y. My equation was 2.5x plus y equals 15. I'm going to rearrange this to solve for y by subtracting 2.5x from both sides. I get y equals negative 2.5x plus 15. What connections, if any, do you notice between your new equation and the graph? My slope is negative 2.5. Where does the graph intersect the vertical axis is 15. Okay, that's how it works. I start at 15, and for every change in y, for every 1 unit I go down in y, I go over 1.25 units. Okay, so this right here is my slope, to get down to the bottom, and my drawing is terrible. But my slope is negative 2.5. So that means for every decrease in rides, I can ride, or I can play another game. Sorry, decrease in games. I can ride more rides. Goodness, I can't get it straight. Okay, let's look at the explanation here. If the student played no games, they can get on 15 rides. For every additional game that the student plays, the possible number of rides decreases by 2.5. We can't decrease by 2.5 rides. So really be for every additional 2 games the student plays, the number of rides decreases by 5. Okay? For every 2 games they play, the rides would decrease by 5, which is about right there. That would be 10. Okay, so I did not draw that well. So really I should be over 2 down 15 to 10. 2 more would be 10, 9, 8, 7, 6, 5. And then 2 more would be down to there. We're not going to try to draw that. All right, we get the good idea though. So this right here is actually my equation for the line. On the graph. Good job. All right, let's do the next one. So this, we're going to do number 3. I have x plus 4y equals 28. So what's the number of rides the student could get on if they don't play any games? And if we remember, x is games, which I can say is true because that's my x-axis and it's labeled number of games. Y is rides, which is true because this is my y-axis and that's labeled number of rides. What's the number of rides the student could get on? So it's y if they don't play any games. So if that's 0, we can divide both sides by 4, and the answer is 7. Okay, hold on. So I love how I did all that. So let me write this first. So if this is 0, I'm going to divide both sides by 4, and y is 7. So on the coordinate plane, mark the point. 7 is right here, and its ordered pair is 0, 7, because I put 0 in for x and got 7 for y. What's the number of games the student could play if they rode no rides? Okay, so x would be 28. We label that here. We're going to have 28, 0. That represents 28 games, 0 rides. I assume the next page is going to tell me to draw a straight line. Cool. So draw a line. Now complete the sentences. If the student played no games, they can get on, so 0 games, they can get on 7 rides. For every additional game that a student plays, the possible number of rides decreases. Let's see what it decreases by. So every additional game, so if I do plus 1 game, which is my equation, it decreases by a fraction. I think it's a 1/4. Double check. Yep. Okay, it decreases by a 1/4. So for every additional game, my slope decreases by a 1/4. So plus 1x gives me minus a 1/4 y. And that keeps on going. So what is the slope of your graph? Where does the graph intersect? So for the slope, I'm going to go ahead and calculate it with my ordered pair of 0, 7 and 20. That's not right. It's 7, 0. Nope, 0, 7 and 28, 0. So I do delta y, or change in y, over change in x. So let's do 7 minus 0. I just did 7 minus 0 over 0 minus 28. 0 minus 28. And that gives me negative 1/4. Okay, and where does the graph intersect the vertical axis? At 7. Okay, that's the intersection of the y-axis or the vertical axis. So now let's rearrange the equation to solve for y. I have x plus 4y equals 28. So let's subtract x from both sides because I'm trying to solve for y. And I have 4y equals negative x plus 28. Divide everything by 4, all the pieces and parts. And I'm left with y equals negative 1/4 x plus 7. And what connections do you notice? Well, I notice that my slope is negative 1/4 and my y-intercept, or my vertical intercept, is 7. The symbols we use for slope and vertical intercept are M and B. I don't know why. I know M. M's always been slope. I don't know why it's M, but it's just M. And B is my y-intercept. I don't know why. We could say a poem. I don't know why she swallowed the fly. Perhaps she'll die. But how did you find the number of possible rides when the student plays no games? I pushed 0 in for x and solved for y. How did you find the possible number of games when the student gets on no rides? I put in 0 for y and solved for x. Where on the graph do we see those two situations? Well, it's on the horizontal and vertical axes. That's where we see the two situations. Okay, we see them on the horizontal and the vertical axes, because where x equals 0 is where you cross the vertical axes, and where y equals 0 is where you cross the horizontal axes. The three equations are all given in the same form, ax plus by equals c. That's called standard form. What information can you get from an equation in this form? What do the a, b, and c represent in each equation? Well, c is my constant. There's no variable with it. A and b, they're both my variables. And I don't know what else I would be able to tell you about that. Oh, so they're my variables. A would be the cost of x, which is the games. B would be the cost of the rides for one ride. Cost per ride, cost per game. And C is how much money, the amount of money the student spends. If we rearrange the first equation to solve for y, we get y equals 20 minus x. We didn't do the first equation. I would have written it negative x plus 20, where my slope, well, it says, is the graph of this equation different from the original equation? The original equation would be x plus y equals 20. These are equivalent. Okay, I've not done anything algebraically incorrect, so I know the equations are equivalent. I could also say, like they did, 20 minus x. Those are all equivalent. You were asked to complete some sentences about what would happen if the student played more games. How did the graph help you complete the sentences? Well, if the student played more games, that increases along the x-axis. That means my y-axis has to decrease. Okay, that helped me complete the sentences. It doesn't help me as much with slope. If we had drawn the graph accurately, we could have figured out the slope also accurately. But I know that as my x value increases, my y value decreases, which means my line slants down as I go from left to right. Another cool thing is the graph tells me how many rides we could ride when we did 0 games, or how many games we could play if we did 0 rides. That's another really neat thing. Those intercepts, they're called, are very important. There's an S there. It won't draw in. There we go. Where your line crosses the X and Y axis, or the horizontal and the vertical axis, are your intercepts. So they tell you what happens if you're not doing anything of the other event. Cool. Would you have been able to see the trade-offs between games and rides by looking at the original equations in standard forms? I'd say not easily. The graphical representation is very visually pleasing, okay? Graphs are easier if you can graph them. Graphs are easier to read than the equation. Do the rearranged equations still describe the same relationships? Yes, because they're equivalent. And what new insights does this form of equation tell us? Well, when we isolate y, it gives us the form. It gives us the form y equals mx plus b, which is linear form. It's called slope-intercept form because the slope is always the number in front of the x term, and the b is always the y-intercept. We'll say vertical. Vertical intercept. Let's try another one. So Andre's jar contains 85 cents. There are no quarters or pennies in the jar. So the jar has all nickels, all dimes, or some of each, right? All nickels, all dimes, or a mixture of each. Write an equation that relates the number of nickels, N, and the number of dimes, D, and the amount of money, cents, in the coin jar. I'm going to say this is nickels, this is dimes. So 85 cents, a dime is worth 0.1, right? Write an equation. Oh, good. I hope it wasn't a like. All right, let's do 5 cents. Because we're doing 85 cents. We don't need decimals. So 5 cents for a nickel plus 10 cents for a dime equals 85 cents. So there is a good equation. Yep. Graph your equation on the coordinate plane. Be sure to label the axes. So let's do if I have 0 nickels, how many dimes would I have? So 0 nickels, I'm going to do 85 over 10 dimes. That'd be 8.5. Right there. Can we have half of a dime? No. So 0 nickels would be 8.5 dimes. If I had 0 dimes, I would have 17 nickels. I didn't write that here. So if I had 0 nickels, what I usually do is I cover up. Like if I had 0 nickels, I'm going to cover up the n term with my hand and divide both sides by 10. That would give me 8.5 dimes. Okay, that many nickels. So graph your equation, be sure to label. All right, so how many nickels? So I'm going to graph it by just drawing a straight line. That's pretty good. So how many nickels are in the jar if there are no dimes? How many nickels are in the jar? 17. How many dimes are in the jar if there are no nickels? 8.5. Is that possible? No. Okay, there will never be no nickels. There has to be a nickel. So our constraint would be we have to have at least 1 nickel in the jar. Not possible to have 0 nickels in the jar. Could each of these graphs be used to represent the relationship between the quantities? All right, what we see here is a discrete graph because I have dots representing. Notice there's nothing at 8.5, right? Nothing at 8.5 because that's not possible, so I can't put a dot there. And 17 at the total number of nickels if there are no dimes. So that would be 0, sorry, that would be 17, comma 0. And 0, comma 8.5 is not a possibility, so there is no dot there. So is this a possible graph? Like this dot right here is 1, comma 8. So if I plug that into my equation, I would have 5 times 1 plus 8 times 10. And that gives me 85, which is true. So each one of these are distinct dots representing exactly how many nickels and dimes are in the jar. Okay, this is a good one. Now what about this one? It's the exact same graph, but it's a straight line. And this works too. It's a shortcut. I can draw a line even though I can't have half a nickel, even though I can't have half a dime. This line represents my data, and I would just say my constraint would be whole numbers only. Okay, works just great. Now here we put the number of dimes on the x-axis and the number of nickels on the y-axis. No problem, that works. Okay, it's a good one. This is a good one too. And here we have another discrete graph. Discrete just means we have dots representing our data. It's a little more accurate. Takes more time to draw, but it's also a good graph. So suppose you were to express the relationship between the same quantities but in dollars instead of cents. What would the equation look like? Well, we'd have 0.85 as the equal sign and 0.05 nickels plus 0.10 dimes, except we would do X and Y. And that would work. Okay, we just have to change how we draw things. What would the graph of this equation look like? Okay, same. You guys see my text in the corner? Apparently Jack needs a library book. Our x-axis and our y-axis would be fine, so this would be nickels. We would just have smaller increments. Instead of it being well, we could do 1, 2. I would want more space so I could put halves in between. Okay. And why would the graph of this equation be identical? Because the equations are equivalent. All I did was divide equivalent. The equations are equivalent. All I did was I had 5x plus 10y equals 85. I divided everything by 100. So that makes them equivalent. Okay, equivalent equations. So we saw equations in different forms representing the same constraint. For example, x plus 4y equals 28 and y equals negative 4x plus 7 both represent the games and rides that a student could do with a fixed budget. What information about the situation and about the graph can we gain from standard form? If I have y equals 0, that'll give me my x-intercept. If I have x equals 0, that will give me my y-intercept. And what information does the slope-intercept form? Well, that is, actually, let's rewind. Well, slope-intercept form gives me my slope in M and my B right there staring at me. So this is graphical what to do. I like it because I can graph it very easily. But let's rewind to this one. This one gives me details about the problem. Like how much the rides cost, how much the games cost. And I think that's it. Yep, I need to go. We're good? All right.